Welcome to the next lesson on structured data in Java, where we take a closer look at Java Collection Framework's ArrayList class, which provides a powerful array-like data structure that provides direct indexing of any element, yet it has the ability to grow as needed while an app is running. After completing this lesson, you will understand the key characteristics of an array list and what makes it a useful data structure. You will also know its pros and cons compared to built-in Java arrays. In addition, you will recognize common methods that are available to work on array list objects. Finally, you will learn how an array list can be used in practice via an extended example that we will examine in detail. Now that we have learned the basics about the Java Collections Framework, we are going to take a closer look at the ArrayList class, which implements the list interface of the framework. Array lists serve the same purpose as arrays in that they store a sequence of same type elements in contiguous memory locations and allow us direct access to any element based upon its index in the sequence. The biggest difference between the two is that array lists allow the size of the collection to grow dynamically while the program is executing, whereas the size of an array is set once it has been created. So, how does an array list object support direct indexing like an array while still allowing the size to grow? Well, first off, it uses an array as an instance variable inside the object. This array is hidden inside the ArrayList object, and the ArrayList object will store its elements in the array. This allows the ArrayList to support direct indexing of its elements. But because the array is hidden inside the ArrayList object, the object is free to replace it with a larger array whenever the need arises. It can accomplish this by allocating a new, larger array, copying all the data into the new array, and then replacing the old array with the new one. And we continue to use zero-based indexing with array lists as we did with arrays and strings. Since an array list is storing data in a private array, it needs to keep track of two properties. One, the logical size, which is the number of elements it is actually storing in the array, and two, the physical size, which is the actual size of the array. Now, the size method will tell us the logical size of the array list. Thus, we can know how many elements to iterate over if we want to write a for loop. The array list does not have a method to tell us the physical size of the array, but that is okay since we really don't need to know that information. All we need to know is that if we fill up the physical array, then the ArrayList object will automatically allocate a new, larger array. When an ArrayList is initially created, its logical size is 0 since it is empty, and the object will keep track of its size as elements are added and deleted. When we compare array lists against arrays, we have already mentioned that their main selling point is that they can grow or shrink automatically as we add and delete elements from the collection. But there is more than just that. Array lists make certain tasks much easier since they take care of many of the details for us. This includes inserting and removing elements from any place in the collection. When we add an element into the middle of a collection, the existing elements must be shifted up to make room for the new element. Or when we delete an element from the middle, the subsequent elements must be shifted down to fill the vacated spot. Array lists handle all of that work for us. Also, the array list provides some searching functions that do not exist for arrays, which can also make things easier for us depending upon the type of search we're performing. I do want to note that the two are about equal when you need to process all the elements of either an array or an array list, as in each case you can write a simple for each loop or a standard for loop. Well, given all these advantages of an array list, why would we ever want to use a plain array? Why not always use array lists? Well, besides the fact that arrays have been around forever and not all programming languages have array lists, there are a few reasons one might still want an array. First, array lists are a little less efficient than an array. The difference is not big enough that it would make an impact on most applications, but if you are writing some time-critical code, then you might want to use an array instead. Second, we lose those nice square brackets that allow us to easily access elements of an array. With array lists, you must use method calls rather than the square brackets. Third, array lists are one-dimensional. and although creating multi-dimensional array lists is possible, it is a bit tricky. And finally, since array lists are a part of the collection framework, they only hold class-type elements. This is not as big of a problem as it once was, as Java now has wrapper classes for integers and doubles that will automatically convert to and from the primitive types int and double. So to summarize, there are some reasons why someone may want to stick with an array over an array list. But for most applications, an array list is probably the better choice for its ease of use. So, besides giving us those convenient square brackets and the length field from which we can tell how big an array is, arrays do not offer many tools for manipulating them. Rather, we, the programmer, must write code to explicitly manage the elements of an array. In comparison, array lists have a group of very helpful methods that can alleviate us from the task of managing all the elements ourselves. We will consider some of the methods in the following slides. First, let's talk about adding new elements to an array list. The add method will handle that for us. There are two versions of this overloaded method. In the first version, you simply specify the element you want added, and it will be added to the end of the list. In the second version, you specify the element and the index where you want it inserted. In this case, all subsequent elements are shifted up to make room for the new element. Note that when you add an element to an array list, we always increase the size of the array list by 1. Similarly, there are two ways to delete an element from an array list. In the first, you specify the object you want deleted, and the first occurrence found will be removed from the array list. In the second, you specify the index of the element to be deleted. In both cases, if there are any elements that follow the one deleted, they will be shifted down to fill the vacated spot, and the size of the array list is reduced by 1. If you want to retrieve or change an element of the array list, you use the get and set methods respectively. They both require that you specify an index for a currently existing element of the array list. And as has been mentioned before, the size method returns the number of elements currently being held in the array list. And here's a quick summary of some of the main methods of the class. In this table of methods, we have already covered the methods add, get, set, and size. The isEmpty method tells us whether the list is empty or not. The toString method returns a string representation of the elements in the list. The remove methods have been covered. The indexOf method takes a target value to look for and returns the index of the first occurrence of the target, while lastIndexOf returns the index of the last occurrence. Both return a -1 if the target is not found. The contains method returns true if the target parameter is found anywhere in the list. And the contains all method takes a list of targets as a parameter and checks to see if they all can be found in the array list. The equals method will compare the array list to a parameter list to see if they are equal, that is, they contain the same elements in the same order. The ArrayList class has two methods that can return iterators. One that returns a normal iterator, and one that allows us to traverse the list both forward and backward. The clear method will remove all elements of the list and set its size back to 0. That is just some of the methods provided by the ArrayList class. As you can see, these methods make array lists so much more powerful than simple arrays. As was discussed in the prior lesson, whenever we create an ArrayList object, we should use the list interface as the type of the variable. For example, if we create an array list of strings, we should assign it to a variable that is declared to be a list of strings. This will allow us to easily change our code in the future to use a linked list rather than an array list if doing so would be beneficial. This is not required, but it is highly recommended. You will understand the reasons for this when you get to Module 7 of this class. And before we get to our final example, it should be noted that the array list has an alternate constructor which allows you to specify a desired size for the array that is hidden in the object. This is helpful when you know the approximate number of elements you want to store in the array list, as it will help avoid some resizing steps as elements are added. Note that even if you specify a size, the array list will continue to grow if necessary, and that the specified size is just a starting size for the physical array. Finally, let's consider an extended example of using an array list. Consider the game of Hangman. Most of you are likely familiar with the game, but just in case, let's do a quick review. One person thinks of a hidden word and tells the other person the number of letters. The other person then attempts to discover the word by guessing letters one at a time. For each guess, the first person either tells the guesser that the letter was correct and where the letter belongs in the word, or the guesser is informed that the letter was a miss. The game is over when all the letters of the word are discovered and the guesser wins, or when there are 6 misses, in which case the guesser loses. Now, we are not going to develop a complete hangman game, but rather we are going to develop a couple of methods that could assist the guesser. In particular, we are going to create an array list that will hold a collection of the possible words for us, and then we will write other methods that will remove words that either contain an incorrect letter or that are missing a required letter. We will start by writing a method that will load an array list with a collection of possible words. For this game, we will use the official Scrabble Player's Dictionary. Since reading in all the words from a file is non-trivial on Android and beyond our current skill level, we will assume someone else has read all the words from the file into an array of strings, and that array is then given to us. Note that we will not load the entire dictionary from the array into the array list, but rather only those words that are the same length as the hidden word. Using an array list for this task is a good choice since we really don't know how many words we will be loading ahead of time, and so it is important that the array list can grow as needed. Let's start discussing the code by examining the method header. The method is called loadWords, and it takes 2 parameters. 1, an integer that represents the length of the hidden word, and 2, an array of strings containing all the words from the official Scrabble Player's Dictionary. And we see that the method returns a list of strings. In the body of the method, the first thing we do is to create an array list of strings, and we assign it to the variable words. Since the official Scrabble Player's Dictionary contains about 80,000 words, we create an array list with an initial physical array of 1,000 elements. We then have a for each loop that processes each word in the parameter array. And for each word, we test to see if it is the same length as the hidden word. If it is the same length, we add it to the array list. When we are done, we return the array list to the caller. Next, let's say the guesser made a guess and is told that they uncovered one of the letters of the hidden word. At this point, we want to remove all the words from the word list that do not have that letter in the given position. We will write a method to do this. The method will take 3 parameters: the letter that was uncovered, the position of that letter, and the array list. Note that if a guess uncovers 2 instances of the same letter, we would need to call this method twice, once for each position. And here's the code that will do that. The method is called must-have-at, since we are requiring that each word must have a letter at a given position. The method takes the 3 parameters we discussed on the prior slide. In this method, we will be removing the words from the array list. When we do this, all subsequent words get shifted down to fill the vacated entry. This causes problems for us if we were to traverse the list from front to back, since if we advance to the next element after deleting an item, we would have failed to test the element that just filled the vacated spot. A simple way to address this problem is to traverse the list from back to front. Then, when we move to the next element, we will be accessing an element that was not affected by the shifting of data. So looking at the body of the method, we have a for loop that iterates from the last index of the array list, at position size of the list -1, down to index 0. In the for loop, we get the word at that index, and then test to see if it is missing the desired letter in the given position. And if so, we remove it from the list. We have a little extra check as well to make sure the word is long enough to have a letter at that given position. When the method ends, the array list that was received as a parameter has been changed, and the caller will see those changes. Finally, let's say the guesser made a guess and is told that the guessed letter does not appear in the hidden word. At this point, we want to remove all the words from the word list that contain that letter. The method to do this will take 2 parameters, the invalid letter and the array list. When writing this code, we will use an iterator rather than writing our own for loop as an example of an alternate solution strategy. Here is the method must not have, which will remove all words that contain the letter the answer is not allowed to have. We start by creating an iterator that will iterate over all the words in the array list. And while the iterator says we have another word to process, we get that next word. We then search that word for the invalid letter using the indexOf method. The indexOf method will return a non-negative value if the letter is found, in which case we remove it from the collection by calling the remove method on the iterator. Notice that for this application, the array list is an excellent choice since it can grow as large as needed when we are adding words, and it has the ability to shrink back down as we delete words. And at any point along the way, we can easily print all the words that are still in the array list to see all the remaining possibilities for the hidden word. This lesson took a close look at the array list class from the Java Collections Framework, which provides a powerful array-like data structure that can grow as needed while the program is running. Now that you have completed this lesson, you should understand the key properties of an array list and what makes it a useful data structure. You should also recognize its pros and cons compared to a Java built-in array. In addition, you should now know common methods that are available in the array list class. Finally, you should have learned how an array list can be used in practice via an extended example that we examined in detail.